Srihari, who is an assistant professor at NIT Surathkal since 2013. He has done his PhD from Andhra University in 2012 and Masters in Science from University of Plymouth, England in 2002, and has done his Bachelor's of Technology in stream of ECE from Sri Venkateswara University in 2000. His significant publications include 4 international journals and 3 international conferences. The 4 international journals are Comprehensive Track Segment Association for Improved Track Continuity, Rough Fuzzy Joint Waveform Agile Sensing Approach for Tracking Benchmark in the Presence of ECM using IMPDAF. His international conferences include a high-speed complementary pulse compressor and its implementation of FPGA, all neighbor fuzzy-related data association.
Because that much big introduction is not required. Actually, students are all waiting. So they are all about publications. Anyway, thank you for introducing. No problem, sir. Because what happens, already I came around Vikram is taking, and I came at 4:03, and again I entered at 4:15, 4:10. So that introduction is sufficient.
Harshita, just conclude.
Conclude.
Yes, sir. Before we begin this seminar, I would like to express my heartfelt gratitude to our principal, Dr. SHV Prasad Rao Garu, and CH Srilakshmi, head of the department ECE, and all the coordinators who sincerely committed to make this event a successful one. I ensure this seminar will be profitable and fruitful for everyone present here. Thank you, one and all. Thank you, sir.
Thank you, Harshita and Prasad Rao Garu. Very good afternoon to one and all. So actually today's agenda is to briefly, because the students, the final year students are the kind of students. Could you please tell me, sir, principal sir or Madam Srilakshmi, who are all the students, second year or third year, or everybody is included? Hello. Hello, everybody is included. Hello, can you hear me? Okay, everybody is included. All ECE students are what? Okay, no. I am just asking final year or third year students. Just all years. Okay, all years. Very good. Yeah. So anyway, why I am asking is, you can just see my title is Drone Detection using IWR 6843, a radar sensor. Usually, whenever we try to detect anything of that magnitude, because I'll talk about that one in a while. You can just see my topic is that one. So with that topic, I'll try to go into a radar topic. So you can just see, because I will be using this one only, so that board only, so that we can be able to drone detection. So basically, what is radar? Radar is radio detection and ranging. Radio detection and ranging. So it evolved just before World War, and then World War II, 1939 to 1945. In World War II, it was the idea was conceived and deployed also. So originally it is meant to detect aircraft. So this is a typical scenario. You can just see. I'm just showing a tower, an antenna, and a target. Today's news, you have seen a car is flying, isn't it? So that is a new era in terms of this fiction. Only in James Bond movies you can see that the car goes to an aircraft comes back to this one. Then when it is landed on a water, then it will become a kind of ship kind of thing, or boat. So similarly, that time they found a mechanism that, the radio waves will go and come back, in the sense that whenever there is an object that it is getting attached with, in the sense that whenever radio electromagnetic wave goes, impinges on a surface of a particular metallic object or any type of material that it is made up of. So a sufficient amount of re-radiated energy will be coming back in all directions. So I hope you will be knowing what is electromagnetic wave. So I need not talk about that one. So that one will go E field and then the H field, and the other direction is the one, because if it is the wave which is traveling like this, then this may be E1, this may be H1. So other two are perpendicular to each other. Such a wave would go, and then based on the power that is being transmitted here, and also based on the gain that it has, usually for a monostatic antenna, the GT is equal to GR. Gain of the antenna is transmit antenna is equal to gain of the receive antenna. So GT is equal to GR. Then the received power is represented in terms of PT, GT, GR, lambda square, sigma by 4 pi whole cube r to the power of 4. This is a equation derived out of mathematically modeling the physical phenomenon, whatever is happening over here. Because I am not deriving that one, I would like to represent that as a simple thing. This is the incident power density, and then backscattered power is based on the incident power density times the radar cross section. This we call it as, so PB by QI. So this radar cross section is known as RCS. RCS of a target is defined like this: ratio between the backscattered power and the incident power density, and that is represented with sigma, whose units are meter square meter, and it is not a physical area. It is not a physical area. Earlier, it's like earlier car flying and like an aircraft was a fiction, but now it is in reality. It is experimentally proven. I think 128 times he traveled before coming into the news, and then 300 kilometers per hour it is traveling the speed. So it is reality now. So like that, the fictional area, this is not a physical area. So it's a fictional area we are considering. That fictional area depends upon, how it depends upon size of the object. And secondly, it depends upon type of the object, type of the material, or the type of the target. And also shape. Another one is shape of the target that you have. The fourth one is polarization of the incident wave. Polarization is, if you remember or not, I do not know. So those who know, who studied this EM wave, and then in a proper manner they will be knowing, it's the orientation of the electric field that we call that as a polarization. If it is horizontal, then we call it as a horizontal polarization. If it is vertical, we call that as a vertical polarization. If it is consisting of both the components with equal magnitude, then we call that as a circular polarization. If both the magnitudes are different, and then it may consist of an elliptical polarization. These are the classifications associated with the E field, electric field, circular and then elliptical. So you can just see, this is the compact representation of a radar range equation. So now let us go to the current situation. On June 27th, you might have seen. Are you all following, or any doubts for anybody so far? On June 27th at 1:30 in the night, India-Pakistan border, and then there is a Jammu air base over here. And then two drones, maybe optocopter or quadcopter kind of shape, They just arrive with some kind of payload carried across the border. That is what they are believing it to be. And then entered into this fence. And because what happens, these people are equipped with a lot of radars, because air base means you can imagine they have sophisticated radars that are being present, and then they're all surveilling in all directions. Even before line of control, anything that magnitude, for example, if an aircraft comes, these radars would have alerted, and then immediately our countermeasures would have taken place. Since these two, whatever the quadcopter kind of shape that came in, are made up of very light in material, maybe a few kgs, 5 kg drone or a 10 kg drone, which is carrying around 1.5 to 2 kg payload. That payload is typically the IED, the explosives, that improvised explosive device that they carry. And then, so this is actually these kind of fellows are called rogue drones. That means they are not a proper ones. So you can make them as so people in the literature called them as rogue drones. So they can come and they can come to any place. Here they only sent 2, because if many sent, then they know the retaliation would be very strong. So they can come in 100 number, they can come in 1,000 number, they can also come in hundreds of thousands of drones. If they come like that, then you imagine the situation of across the line of control in the east and west. So what is the new challenge for this one? Are you all there now? Hello? So I need at least 1 or 2 persons responding. Otherwise, I do not know what is happening the other side, because I am looking at the board and teaching, isn't it? So somebody should respond, either a teacher or other. Any voice problem is there, or communication. Hello. Okay. That's all. Thank you. So now, how to detect these fellows? There is no comprehensive technology associated with detecting these fellows. So radar is one fellow, but the radar is designed for typically, because I told you just now, these kind of fellows would have a cross-section sigma that is of the order of 0.01 meter square. For some drones, it may be UAVs 0.1 meter square. Some nano drone, it is 0.01 meter square. So I'll just show you our results, whatever experiment that we conducted in our startup. And with that, we detected a nano drone at using some 60 gigahertz radar, which we procured from Texas Instruments. Okay. So we did some experiment, because this drone what we procured of this RCS is of weight 100 grams. And it is controlled by a 2.4 gigahertz remote control. And using remote control, I can operate, then it can go to up and elevation and all that. There is no GPS, there is no camera. The next versions we are going with GPS and with camera, how we can try to detect such kind of targets. Next experiment is that one. I'll just show you some slides based on that. So the major challenge is, as the sigma is diminishing, the received power is less, so we will not be able to detect. And also, many of the radars are pulsed. Many of the radars, whatever in JEMO place that are there, are pulsed. So why they are not able to detect this kind of target, I'll just tell you. So what is a pulsed radar operation? Pulsed radar operation goes like this. Okay. Pulsed radar operation goes like this. This is the tau. This is the time period that we call it as a PRI, pulse repetition interval. So if this tau is 1 microsecond, then C tau by 2, the radar ranging principle, goes with a typical this diagram only. I'll just go back here and then explain the ranging principle. Suppose if this electromagnetic wave, whatever is you released, has to travel a distance of r, then the re-radiated energy from that particular target which impinged on that also should have come back in the R direction only, because it is monostatic in nature. Then the total distance traveled is 2R. And if you say that time elapsed between the transmitted and receiver is because if you assume that your target is received over here, this is the T0 instant of time you receive, then the 2R is the distance that is traveled. C is the velocity of the light at which it is traveling. T0 is this one. Then the range can be determined by C T0 by 2. Same principle is also applied for this one. What is this one? Because I have a transmitter. So this transmitter started transmitting this waveform. This waveform is a pulsed waveform. If you assume inside that pulse, I have a waveform. So that waveform is like this. So what is happening? This is a trailing leading edge of a pulse, and this is a trailing edge of a pulse, and in whose duration is tau seconds. Until or a tau microsecond or whatever, tau units seconds. So tau can be 1 into 10 power minus 6, so like that kind of thing. Here we have taken 1 microsecond. Tau could be 1 microsecond. Let it be 1 microsecond. So until 1 microsecond time is elapsed, so you are not releasing the waveform. If you are not releasing the waveform, where is the chance of that waveform is going and coming back? So only after 1 microsecond elapsed time only, you will be able to see that presence of a target. So what happened? So typically they are telling 14 kilometers is the border distance between that base and then the Jammu Air Base, LOC and the Jammu Air Base. So you can imagine, suppose 1 microsecond pulse radar, if that radar is using, then associated distance is 150 meters. This 150 meter is known as blind range. These pulse radars are not equipped to see beyond within 150 kilometer of this radar vicinity, 150 meters of the radar vicinity. So hence the radar is blind range. Suppose if this 1 microsecond is an example. Usually it is not. 1 microsecond is 10 microsecond if you consider, then this is again multiplied by 1500 meters. How this has come? 3 into 10 power 8 into 1 micro is 10 power minus 6 by 2. I used ranging principle. From the ranging principle, I evaluated it as 150 meters. If it is 10 microsecond, then it goes. If it is 100 microsecond, what is 100 microsecond? 1 millisecond. If it is 1 millisecond duration, 1 millisecond duration is very large. 1 millisecond duration is almost like, 15 kilometers. That means until the line of control, it will not see anything, because even beyond, within 1 kilometer of Pakistan also it cannot see. Then it is more dangerous. So they might not have fixed it like that. So 10 microsecond, 1500 meters. The 1500 meters are 1.5 kilometer, 1.5 kilometer. Maybe instead of releasing by Pakistan 1.5 kilometer away from there, some anti-social element within that Jammu and Kashmir might have released that, and therefore the radars which are available here will not be able to see them. Then how to detect them? So where is the technology? Is there only that technology or any other technology? Yes, there is another radar that is available that is known as CW radar. What is this CW radar? CW radar is equipped with a transmitter and a receiver. Obviously, when we are transmitting, that local oscillator signal is fed to the receiver. So here is a mixer, then the LNA and all that post processing you can do. So there is an antenna, transmitting antenna, there is a receiving antenna. A rough black diagram I'm trying to draw. So in CW mode, continuous wave radar, this is. I will be continuously transmitting that waveform. In the receiver, I will be getting a received waveform of either this nature or a received waveform of slightly compressed version of this. So what is this thick blue fellow represents? So this is if this fellow has a frequency FC, This fellow might be having a frequency Fc minus Ft, or this fellow might be having a frequency Fc plus Ft. In total, this could be Fc plus or minus Ft. It depends upon whether the target of interest, because the target you are looking at, whether it is approaching or the receding. If it is coming towards the radar, if it is coming towards the radar, then it is Fc plus Ft. If it is going away from the radar, if it is coming towards this one is this one. If it is going away from the radar, then Fc minus Ft. You can understand this concept by using an ambulance. So ambulance is there, and then these days very popularly they are all going because of the pandemic situation. You can observe. So this ambulance, when it is coming towards you, you can see a huge difference in the hearing. That means the siren you can hear more often than when it is leaving from you. That more often than is known as Fc plus Ft. Less often than when it is approaching you is known as Fc minus Ft. Therefore, you will be able to hear that kind of perceptually, that kind of difference you can observe, and then that is what is observable. So, what is this Doppler shift? Fd, if I get what I will get. Mathematically, you can prove that Fd is equal to 2V by lambda. If it is theta is 0, or Fd is equal to 2V cos theta by lambda. The cos theta is the angle at which it is, because if you are seeing the both side of the antenna, then it is theta is 0, then it is 2V by lambda. If it is not looking like that, then it is 2V cos theta by lambda. Okay. So what we now see is what are the current applications of this radar. So everything is fine so far now. Hello.
Yeah, it's okay, sir. Sir, I request the organizers. I think, sir, please give permission for the people to unmute and ask questions, sir. Yeah. So, participants, మీకు మధ్యలో డౌట్స్ ఉంటే దయచేసి అడగండి.
Okay. So anyway, let them ask any point of time. There is no problem. Now, earlier case, what was the problem is that we will only be detecting the Doppler and the velocity. But now, because of the advancement, one of the technique that it is there since a long period of time. This kind of radar people call that is a LPA radar. This low probability of intercept radar is for short range. So short range is typically less than 5 kilometer range or less than 10 kilometer range. If you want to detect something, range as well as Doppler, so people were deploying this kind of radar. So usually the frequencies at which these radars operate are, as I told you, the chain home radar initially World War II they operated at 30 megahertz. Then VHF band 30 to 300 megahertz. UHF 300 to 1 gigahertz. Then L band 1 to 2 gigahertz. 2 to 4 gigahertz. LS C band 4 to 6 gigahertz. 4 to 8 gigahertz. Yeah, LSC, and then next fellow is 8 to 12 gigahertz, X band. Beyond that, they are all going. But if you see a 10 gigahertz fellow, a 10 gigahertz is C is equal to F lambda. If you try to see, it's lambda 3 to 10 power 8 divided by 10 gigahertz. So how much is that? 0.03 meters. Okay. So that is the wavelength at which we are operating. Okay. So we are at 10 gigahertz. So what we are trying to do here is now, as the frequency of operation is also important because it all depends on a lot of other parameters, because When I told you earlier, this this PR is also included K T naught FB. There is one more fellow that is known as noise power. There is one more fellow that is incorporated over here is LS, the system losses. The system losses depends upon what kind of frequency that you are operating, what are the operating, what are the atmospheric losses, what are the other system losses that encountered during that process will also be incorporated in this one. So earlier, why radar did not determine range? Because ranging principle requires some kind of gap here. Only that elapsed time is present, then you will be able to determine. What people did in FMCW radar is they cleverly modulated the frequency to a reasonable extent. That is, the modulation is done using a linear FM technology. That linear FM is, you all know the frequency modulated signal. So they linearly increased the frequency. That is, if the waveform is like this, then as the time progresses, the waveform is compressed like this. So in the sense that the time is diminishing as the, so that frequency is increasing linearly. So the kind of radar that we were talking about is 77 gigahertz to 81 gigahertz. This is one example that very famous radars are there. Actually, Vandana, my employee in that startup, she will be presenting today, showing this 77 gigahertz radar also to you through the video, the second part of my lecture. She will be demonstrating what, how we applied these things, and then she will also be showing the 60 gigahertz radar that is used for drone detection and other things. Actually, I will come to that one, but before that, this is the principle that we normally apply. So here, if you just see, this is the received signal that you will get. This is the time elapsed. So what is that you will be able to know here, because the slope is known to you. The slope dy by dx, the df by dt is slope, some k is there. That k is known to you, or k or s, because in automotive terminology, the TI people determined that as s. They christened the name, they have given it as s. So therefore, you can just see delta f by delta t is equal to s. So this is the slope that you have. And then once you know this delta t, the time elapsed between the transmitted wave and the received this fellow like this, then you will be able to determine, because slope is known to you, the delta f can be determined. Or since the slope is known and the frequency difference is also known, you can determine the delta t. Okay. Once the delta t is determined, because if you want to determine this delta t, you can use in this one. Once the delta t is determined, because it is simple formula earlier, whatever 2r is equal to c into delta t. So the range can be determined c into delta t by 2. From the slope, you can determine the delta t, because delta t is equal to delta f by s. Delta t is equal to delta f. Simple dy by dx formula only. The slope is known. So like that, you will be able to determine the range in addition to the Doppler. Anyway, Doppler will be determined based on the, because you have two transmitters, one transmitter and one receiver separately. And then whenever a moving object is present in front of it, you can determine the Doppler. So since Doppler can be determined, what we have done is 2 experiments that she will be showing to you now. Because I don't want to tell more and then maybe confuse you with a lot of slides and other things. The lecture is very simple. So idea is you should be interested in this domain, and then thereby you will be further learning it. A person like me coming for 1.5 hours and then maybe you may feel that everything you can learn is not possible. So only thing that you can learn is such and such things are available in electronics and communication engineering. If you put some effort, we will be able to learn such kind of concepts and other things. So one thing is we are focusing is heart rate and breath rate experiment which we have done. and the other one is drone experiment, which we have done. Specifically, this heart rate, breath rate experiment, what we have done and how we have done this, we used 77 gigahertz radar. It is FMCW in nature, short range, whose maximum range is 100 meters. For the drone detection, we used again from Texas Instruments only. In maximum range here also around 100 meters. So these two I will be explaining and then showing it to you. So give me a second, I just come back. So before the drone detection fellow comes into existence, let me talk about the other, that is heart rate and breath rate experiment. Okay. So give me a second, just I represent my screen. So this is the screen that I am sharing it to you now. You can just see this is the radar that we used. So you may ask a question, is it a radar, sir? Because radar means we thought a big one. Because if you Google radar, images come very big. But if you Google automotive radar, then they are all very small. They work with millimetric wavelength, 77 gigahertz. If you try to find out the C is equal to F lambda, then you can try to come about what are the wavelengths that it is operating. So 77 gigahertz, you can just see 10 gigahertz only we got the 0.03 meters. So if you go with 77 gigahertz, you will get a millimeter of wavelength, the lambda is. Again, the antennas are designed with lambda by 2 separation and all that. So this is a very powerful radar, powerful in the sense that it is MIMO in configuration. That is multiple input, multiple output radar that consists of 2 transmitters and 4 receivers, and everything goes into the chip that is connected on the upper side. You can see 2 transmitting antennas slightly separated away, and then 4 receiving antennas. Anyway, Vandana will explain with the help of the board what where the radar is present, and radar on a chip is. So using that, it has a DSP processor and a microcontroller thing, and then other data ports, and then there are many other facilities that are embedded into this board for various other applications that we can develop based on this. That ARM Cortex microcontroller, then C674X DSP processor, and such kind of fellows are available over there. So what we have done is we did an experiment using this. That experiment is this one. So we kept that one, and including myself and then few other volunteers came in front of the radar. So we measured the breath rate and heart rate without touching the person's body. That means he's away from 0.3 meters from us. So there is no connections that are established, because the radar is a wireless device, you know. It is transmitting power and then receiving some power back. So therefore, you can just see how we can try to understand such kind of things over there. Okay. So now, so it is like after doing that experiment, what we have got is, so after doing that experiment, what we collected is, we collected the heart rate, breath rate of a person. So by using these parameters, and this is the algorithm that we used. Again, here we did with the help of others. It's a giant publication actually. So with 24 gigahertz is already accepted in a conference, and then 77 gigahertz we are trying to send it to another conference here. So this is a typical algorithm that we applied and used a band pass filter, FFT peak detection, then the FFT peak detection, then the heart rate and breath rate is calculated. So experimental results only, these are not simulation results. Heart rate per beat is beat frequency into 60. This is the one this we will try to do. So and then heart rate for another subject is also listed here. And using these results, the 4 received data is tabulated, and the average value is also calculated here by using the same radar module. So like that we can do with the other sensor also. That also we did it. So we are not. I think what's Vandana's plan, I do not know what she's going to show, because in our startup she is developing a lot of products. Actually, she's a product development manager, so she is going to talk on these things. Actually, she is only presenting the paper which is got accepted by using this sense to go pulse also. So maybe I think briefly, because demonstration she will show, and then you can just see how the results are coming into it. So these are all other sensors are also there. We are not going into those details. So now the actual topic I will do another 10 minutes and then close, because I decided to do only 45 minutes of mine, and then rest of it is done by Vandana to give you the more practical exposure. Because as I told you, we started this startup last year, and then she is working for us. And since then, last 1 year, we have developed a lot of things. And then in every project, she is involved, whatever we were doing. And recently, we engaged with a lot of other projects, which we are trying to do with even with Indian Army. We are working on several projects for future development. So in all those things, so we are working with kind of this thing. So you can just see a lot of other civilian applications also we are focusing, and besides developing academic products for engineering students, wherein they can be able to do experiment themselves over there in the college itself before leaving to the. It's an additional tool because it is not part of the curriculum. If some colleges are interested, we are also giving it to them. Anyway, it's a separate thing. This IWR 68143 is a separate device. It is not 77 gigahertz. So these are all some kind of introduction I don't want to go through. You can just see the drones are a threat to us now. So the drone which we used is this kind of, because drone picture is not there, but she will show you what the picture is. So this is the typical setup that we use. The IWR, then on the PCA 1000 data capturing module, FPGA is required. This is operating at 60 to 64 gigahertz, and 4 transmitters, and then three transmitters and 4 receivers are there. Azimuth field of view is -60 to -60 plus or minus 60. That is 120 degrees it covers. The elevation field of view is -15 to 50. That is 30 degrees elevation it will cover. Gain is 7 dB. And all these parameters are very important for our detection. So this is the experimental setup. When it is connected, only this photograph is taken, IWR sensor. So with that, what we have got is, she will explain what is mmWave Studio and other things. So because I need to close my conversation, otherwise it will be longer for you. And then if required, we will have other sessions. So this blue dot over here is detection at around 5 meters, so 4 meters. This is the range up to 25 meters here. So the graph is showing this azimuth field of view, because I told you azimuth is -60 to 60, but we are only operating close to that broadside array normal. So we are not focusing much beyond that one, because we want our experiment is a primitive experiment, and the drone is also a nano drone with 0.001 meter square RCS, that is 1 into 10 power -3 meter square RCS. So you can clearly see the detection at 5 meters, detection at around 15 meters, that is the second one. We would also be able to detect detection at around 45 meters, around 50 meters. This 50 meters we just shown, but it is not exactly 50, around 50. So these are the references associated with them. These two experiments, both of them we carried out using our own equipment, and this is an experimentation that we have done on the drone and other stuff. So I think I'll be happy to take any questions related to that one, the lecture that I have given. So primarily, to summarize, what I have done is I have briefly given the current surveillance situation, why it failed in the Jammu attack. Radar were not able to detect such kind of small objects because they are of small RCS, and then Also, most of the radars deployed over there are pulsed in nature, so they have blind range. They would not be able to detect the closer vicinity targets. For that, the solution that we need to go for is a comprehensive solution is fusing the data from multiple sources. That is a different story. But radar that needs to be deployed over there is FMCW in nature, that is frequency modulated continuous wave radar. So then I told you the basic radar range equation, how the other parameters comes into existence, what is the Doppler principle that we normally use with using a CW radar, and then we went into continuous wave radar. Then the heart rate and breathe rate experiment is done, and then the drone detection experiment which we conducted, the results are shown, and two radars that we used here are present here. Vandana, are you there? Hello.
Yes, sir.
Okay. So you please take over, and my request to you is show the physical radars so that they will have a feel of it. Okay. Switch on your video and then show the physical radar. So this is a demonstration, whatever is followed by, because the theory, mathematics, physical modeling, your teachers also does. So you focus whatever she is going to do and then see how these are going to add value to you. So today you are learning something new. So if you want to experiment it also, we will be able to assist you if required. So you just think over all these things. You can also buy YouTube videos and then learn a little more on that. So Vandana, over to you.
Yes, sir. Thank you. Good evening, everyone. My name is Vandana, and I have been working as a project development manager at Shri Shasha Prayathi Technologies Private Limited. Uh, right now, I will be sharing with you a video. Uh, okay, with a video of the various sensors that we have here. So, is this window visible? The
Yeah, the window is visible. Yes, window is visible.
So here, now the sensor that you are looking at over here is the sense to go pulse 24 gigahertz Doppler radar sensor. So this is the base board of the sensor, where you can see this module, this microcontroller, that is XMC 4700, which is required for the signal processing of the whatever the radar data that has been collected. And this board has an Arduino compatibility to it also. Now, along with that, the other side of this board consists of the RF module. So here, whatever this you can see the transmitter and the receiver part. So they are patch antennas, an array of 4 array of patch antennas. So they act like a single transmitter and a single receiver. So this is the RF module, and also the field of view is 29 degrees cross 80 degree. So based on our applications, we can set it to 29 degree facing the front, or if you place it in the side horizontal direction, we can get a field of view of 80 degrees. So this is the first sensor. This sensor is a Doppler sensor. It can detect motion and movement, whether the object is moving towards you or moving away from you.
What is the maximum range?
The maximum range is around 30 meters. So the next sensor is the FMCW radar sensor. So here if you see, there are again it is a single transmitter and a single receiver sensor. But here the number of patch antennas is 2 cross 4 array of patch antennas. And again this board comes with the a debugger connected to it, as well as the RF signal processing board attached to it. So here you'll be able to connect the USB port and able to receive data and also for data acquisition. So here you can
Some noise is coming from somewhere.
module.
Hello. Hello.
This one is the sensor which sir presented right now about the drone detection. So this is the IWR6843 ISK. It operates at 60 gigahertz, and the board which you can see behind this radar module is the DCA board, DCA 1000 evaluation module. That is the board where which captures the data. So the USB connections are slots are present, and also you can store the data using an SD card using this DCA board, and whatever the data that has been acquired can be processed in this radar sensor. So this is the 60 gigahertz IWR 6843 module. So this one is the another module that operates at 77 gigahertz, which sir initially spoke about regarding the the AWR 1642 boost. So this board also can be attached to the DCA 1000 so that the data can be captured on it. And this the previous board, that is a 6843, over here you will be able to see the number of transmitters and the receivers. So you can see there are 4 receiving channels and there are 3 transmitter. It is a 4x3 radar antenna sensor. So there are 12 virtual arrays of receiving channels. So similarly, which we can call it as a MIMO radar, that is multiple input and multiple output. Now, when coming to this 77 gigahertz radar sensor, here it is a 4 receiver and a 2 transmitter module. So here you will be having 12 virtual channels. So this board also can be connected to the DCA 1000 board, and we can acquire the data. And this module also we are trying to experiment for heart rate and breathe rate measurements because of the capabilities of this module being the FMCW module. So this is the other side of the board of the where you can connect this module to the DCA board. Okay. So after this, I would like.
Yeah.
Yes, sir.
Yeah. Okay. Vandana, you briefly present your 24 gigahertz results that you are going to present in Connect, because I only focused on 77 gigahertz. You can just tell that is the radar which you first initially presented, no, in the video. That is the radar which you should capture this one, and that paper has been accepted in the conference, and then you are going to present, that same thing. You just briefly 5 minutes, you just tell the students. They can understand the significance. Do you have that now?
It's not like right now I don't have that files.
Okay, fine. You go on. Yeah.
Okay. Yeah. Now moving on, I will be showing you the image of the drone that we have used to present the that we have used in the detection of drone using the 60 gigahertz IWR 6843 module, radar sensor module. So this is the drone, and which it has a very small RCS, and it is very lightweight, around 100 grams. So it is a very lightweight drone model. So so this is the one which we have used for the experimentation. Now let me show you some results using the TI Texas Instruments developed MMWave Studio. So here I have already done the experiments, but I will be showing you the results that I have stored for the drone detection and also the heart rate and breathing rate experiment detections. So now this is the MMWave Studio graphical user interface. Here the setup that you are able to see is the one where we are supposed to set the that is we are trying to configure the radar sensor with the mmwave studio, and we are supposed to give the inputs to the radar sensor, and so that it works according to our applications. So initially we need to do the setups deciding the COM ports and also the operating frequency, because we have two set of operating frequencies like sensor modules with 60 gigahertz and 77 gigahertz. Also, there are different variants of the radar sensor modules, ranging. So each are used for different applications as well. So the two sensors which we are using are the WR1642 and the WR6843. So also there is this DCO board setup communication as well. Since I'm not attached that board right now, we will not be looking into like configuring the setup. I would like to also show you the sensor configuration, like what type of sensor configurations that are required here. So here, if you are connecting it to a 77 gigahertz radar sensor module, the starting frequency will be 77, and as sir explained, for a FMCW radar, the frequency variations will be from 77 to 81 gigahertz. And also we can set up the transmitting time, the idle time, that is the time between each chirps. So here in the small window, they have displayed like what are the different features. So how many ADC samples that we require, and how many number of frames of data that we require, and number of loops. So for one chirp, we can set the number of ADC samples that we receive for. So here I've set up the number of chirps as 128. That means for each chirp, I'll be able to get 256 values, and the number of frames are 8. That means for each frame, I will be getting 128 chirps. So for one frame, I'll be getting 128 chirps, and for each chirp, I'll be getting 256 samples. Also, you can set the other features like sampling rate, then ramp end time, that is at what time the chirp should end. So these things can be decided, and based on our applications, we can change these setups.
Vandana, you give me 2 seconds. I'll just explain how in a frame how many chirps you are keeping. 128, no?
Yes, sir.
How many frames you are sending?
Now 8 frames in this whatever is displayed over 8 frames.
So I'll just you just be there in a couple of minutes. I'll just come back to them. So I hope you can see the students. So since it is an important, I felt that's why I came back actually. You can just see, because it's in complementary way. If you go, that is better. So FMCW radar goes like this, because if you instantaneously take off and then come back, it is a ramp kind of signal. So this kind of thing I am calling as a chirp. Whatever goes up and then come down, it is single chirp. Like that, what she is doing is 1, 2, 3, ... around 128 chirps she is transmitting in a frame. The last fellow is 128th fellow. So all this together is known as frame. Okay, like that 8 frames I am transmitting. Once a frame I get back, because all these 4 receiving antennas will receive all this. That is again a different story. That is the beauty of this radar. So once this particular chirp comes back to you, again with the ADC you are just doing 256 samples. These samples are known as fast time samples. So finally 256 into 128 into 8. This is the kind of dimension that you are looking at in one receiver. In another receiver, again 256 into 128 into 8. Like that 4 receive data you will get it. Okay. Like that 4 receive data you will get it, and associated with the 2 transmitters. This is for one transmitter. So second transmitter again you will get like this 256 into 128 into 8 into 4. So that much amount of data that you are getting for 8 frames. So all the data will contain lot of information that is in front of it with us. That is the actual beauty of this MIMO configuration. Then rest of the task is to do the radar signal processing, or you apply machine learning, or you apply pattern recognition, or you apply deep learning to do the processing of this data. Because you might have heard big data. So like that big data here also a lot of huge amount of data that is coming out of this transmission. So anyway, so if any doubts are there, then I'll be happy to do it. Vandana, over to you, you present it.
Okay, sir. Okay, so this is how we need to set up the configuration. So once that is done, let us go to the post processing of once the data has been stored in your computer. So here now whatever the data I am going to play is where we have detected a drone at 5 meters, and the number of frames that I have used are now 25. So while playing the data, I'll be playing the data now, and you can observe the drone movement, as well as on the heat map you will be able to observe slight signatures based on the drone. So whatever the red dot you are able to observe over here is the drone movement and the drone that is being detected. So if I play it once again, and here you can see some drone movement being appearing over here. So this is the 2D FFT plot where you can measure the distance along the x-axis and velocity of that particular object or target. So which is between 0 to 2 meters per second. And even here in the second plot, that is a detection and angle estimation plot, you are able to determine the distance in meters in both the x and the y axis. That is, the sensor is placed at this 0th position, and the whatever the drone is that we are viewing, it's like we are viewing from a top view. So that blue dot, whatever is the drone that has been detected. And also on the here you can observe the FFT output. So in the times FFT output that can be observed over here. So after applying 1D FFT for each chirp. Also, then the final output window that you can see over here is the real and the imaginary time domain signals. That is, which is the time domain plot. Real is the so in a complex data that we receive, this ADC samples data, whatever we are receiving it in the form of a complex value. So which has real part and the imaginary part. We also call it as the in-phase and the quadrature components. So I and Q components. So the real part is represented, that is by the blue color is the I in-phase component, and the red one is the quadrature phase component. So here also you can see the setups that has been done, the setup for that particular experiment. So the frequency slope and the frequency variation that has been kept at 60 gigahertz, and the slope is being varied according to the total distance that we need to cover. So based on that, these are the setups that has been done. So now let me load another data that has been saved. So that would be a detection at 20 meters. So the detection at 20 meters, I will be displaying it now. Okay. So here you can observe that a green dot appearing on the detection and angle estimation plot. So this green dot, whatever you can observe over here, is saying that that there is some kind of detection at between 20 to 15 meters. So the third one I would like to show is the distance, the detection at 50 meters.
Any video that drone flying is there on the with you? Can you show it to students?
Like, no, sir. Like, right now, I don't have it.
Oh.
So here, if we are able to see a detection at 40 to 50 meters, so again, you are able to observe a green dot over here at a distance of 50 meters. So this is about the drone detection that has been conducted. Now I would like to share with you another detections that is for the human vital sign measurement. So here what we did was a person was made to sit in front of the 77 gigahertz radar sensor, which is an FMCW radar. And here what the person is sitting in a stationary position in front of the sensor, and we are able to observe, and here we are not trying to detect that person, but we are trying to extract the IQ data so that we can process it further and get the micro, like the heart rate and the breathe rate, that is the chest movement. So this because this is a 77 gigahertz, like a very high frequency module, so the wavelength will be of very short wave. So these are short wavelength sensors. Because of that, we will be able to identify very small movements as well. So here, so for that reason, we are using the 77 gigahertz FMCW radar sensor for heart rate and breathe rate measurements. For some reason, I'm not able to display it.
What happened? What is happening? Hello.
Don't know, sir.
Okay. So what is the heart rate, breathe rate you are trying to show?
Yeah, that, like the detection in sitting in front of the sensor.
Okay. Maybe has it got stuck to the laptop?
Yeah.
Okay,
Yes,
no.
now it is.
Yeah.
So here for this, I have collected 10 frames of data, and for each of them, there are 128 chirps. So now when I play this data right now, also the frequency slope is kept at 50, and the module now, whatever we are using, is a 77 gigahertz module. So when we play this data, you are able to see a detection over here, that is a green dot, where that is very close to the sensor. So we have placed this person around 0.5 meters in front of the sensor. And here we are basically concentrating on the time domain plot, the data that we acquire, that is the I data and the Q data. So based on this, we are experimenting to extract the information. So let me show you another detection of the same experiment. So here also you are able to detect a person sitting in like a target in front of the sensor, and also there is also a detection of another person or a target in the same frame. But we are looking into very small frequencies, that is 1 to 3 hertz and 0.1 to 0.8 hertz. So 1 to 3 hertz for heart rate measurement and 0.1 to 0.8 hertz for the breathe rate measurement. So in these cases, we are easily able to analyze, because these are the very like small movements that we are trying to extract from the IQ data that has been acquired. So also here, if you see on the heat map, also can be observed where there is some kind of signatures very close to the zero location. So this is the about the mmWave Studio and the two radar sensors. Now I would like to show you another 24 gigahertz Infineon radar sensor, which has been which is the Doppler radar sensor. So previously we saw two FMCW radar sensor. Now whatever you will be able to see is a Doppler radar sensor which detects motion. So here the basic setup. So the controller board, as I already told, that is the XMC 4700 radar base board, and the RF board consists of this BGT24 LTR11 shield, which is the radar sensor. And it is the mode of operation is pulsed Doppler. So it will it will send continuous wave signals in the form of pulses. So it has got one transmitter and one receiver. So here there are few setups that we can do. It is not as complex as the mmWave Studio setups, where there are multiple configurations that can be done. Here the setups are quite simple, where we can change the sampling frequency, samples per frame, any samples that we need to skip, so that there will be no DC components or non-linearities. So we can do that also over here, and the frame rate that can also be decided, and the DSP settings. So here, since we are able to visualize all the information in simultaneously, so this is done using this XMC 4700 radar baseboard, which can do sampling as well as FFT calculations on its own. So this particular board, now I'm trying to move my hand um, over this particular sensor. If there is no movement, it will not be able to, it will be detect as no motion. If there is any, I'm trying to move my hand away from the sensor, so it is showing it is departing. If I move my hand towards the sensor, it will say it is approaching. So it is detecting motion. So here you can see the frequency spectrum on the top, as well as the time domain data can also be visualized, and you are able to track the motion, and also you will be able to track the whether the target is departing or approaching. So there could be multiple applications based on this detection, that is whether like a door opener or intruder detection coming towards you, so that there could be some kind of warning systems. So there could be multiple applications as well. So this sensor could always be used in intelligent switches, outdoor lightings, and even vital sign detection sensing. So that is the one which we have, the paper that we have published, that we have that has been accepted with the conference. It's about this vital sign sensing using this particular. So so yeah, here you are able to detect the FFT magnitude is being detected, and also the direction of movement, whether you are approaching towards it or moving away, can also be detected. So so yeah, thank you. So this is what I would like to present. And
Okay. Thank you, Vandana.
yes,
Thank you for your nice demonstration. So students, any questions from your end now? Hello. See, now we have seen the practical demonstration of small radars. I think we have at least shown you some 3 different radars. One working at 24 gigahertz, another one working at 60 gigahertz, another one another 77 gigahertz. You can see from the range from 24, 60 and 77 gigahertz, you have seen the range of applications, because these are only very few we just covered, because to make it simple, because there are numerous applications that are present in the literature, they will all be available. So any questions from any students, because all round students are there, so any. Hello. Hello. Vikram Garu.
Sir, can you tell about some internship opportunities in this field?
Yes, but internship opportunities, what happened now? We are experimenting with a couple of students, but what happened now? They are joining, but after that they are not at all turning up. We have to go towards them. If somebody is really serious, then there are a lot of opportunities. As I told you, good amount of students, serious students comes, then definitely we will be engaging them in unpaid internship, in the sense that we will neither take money from them, we will not pay them, but they will be learning a lot in this radar domain with these experiments, and then we will be sharing the data and then writing some reports, good reports, and then analyzing the results, whatever the results that have come, or solving some good IEEE papers, couple of them, or maybe working on real-time problems that we are working in. A lot of opportunities are there, Vikram Garu. But the thing is that students have to come, because our experience, especially because now a couple of our own students are there, they are fine, because our own students means we have control on them, and then it is like they genuinely want to do, and then they have come. If such students are there from this VKR college also, we are interested. Last time, I think from the nearby college, I think we engaged with one MTech student. She was okay, but other than that, in Vijayawada, one college, I don't know the name, students have come, then finally all excuses only. So it's like, I have exam, I have this thing, I have this thing. My parents got into Corona, after that none of them came back. So I don't know. So if any serious students are there, Vikram, definitely internship opportunities are there. Especially if through you somebody has come, then it is like we will give priority to them, and then just like. The only thing is that they have to show their commitment. See, it is like we are providing time, valuable time towards you, and you also provide in such a manner, then it is win-win situation for both. If such people are there, serious students, I don't want any outstanding abilities in learning. So average student is also fine, but seriousness is the one. Bhakti Shraddhalu antaru kada Telugu, avunte sir. So that's all, Vikram. Opportunities are there, but we will filter multiple levels and then take.
So winner kada students, please try to ask some questions. So this is the opportunity for you for doing good projects also. బికాజ్ మీకు తెలుసు చాలా మంది చాలా కాలేజెస్లో ఎలాంటి ప్రాజెక్ట్స్ చేస్తారో, ఎక్కడికో వెళ్తారు, కొనుక్కొచ్చుకుంటారు. బట్ హియర్ ఈజ్ ఏ రియల్ ఆపర్చునిటీ వేర్ యూ కెన్ వర్క్ ఆన్ సంథింగ్ విచ్ ఈస్ రియల్లీ రిక్వైర్డ్ ఫర్ ద కంట్రీ ఆల్సో. లేదు అంటే వీ విల్ ఎండ్ ద సెషన్, దట్స్ వై. ఓకే, రైట్, బికాజ్ ఎవ్రీవన్ ఈజ్ హ్యావింగ్ ఇంపార్టెంట్ వర్క్.
మీరేం మాట్లాడకపోతే మేమేం చేయలేం కదా బాబు. చెప్పండి, తెలుగులో అయినా మాట్లాడచ్చు.
సార్ ఇప్పుడు మనకి డ్రోన్స్ వస్తున్నాయని తెలుస్తుంది కదా సార్, రాడార్ డిటెక్షన్ వల్ల. అది ఏ కంట్రీ నుండి వచ్చిందని ఎలా తెలిసేది సార్?
ఏ కంట్రీ నుంచి వచ్చిందని తెలీదు, ఇది మన సస్పిషనే. ఇప్పుడు ఏందనంటే, మీరు ఒక హిందీ మూవీ మన విజయేంద్ర ప్రసాద్ గారు రాసిన చూసుంటే, బజరంగి భాయిజన్ అని. సో ఈ హీరో పాకిస్తాన్లోకి ఎంటర్ అవుతాడు. ఒక చిన్న పాపను వాళ్ళ అమ్మ దగ్గర ఇడిపించేద్దాం, వాళ్ళు ఇతన్ని జాషూస్ అని పట్టుకొని తిరుగుతారు. అంటే ఏంటంటే గూఢాచారి. సో ఇతను నిజంగా పాపం గూఢాచారి కాదు, అతనికి గూఢాచారి అని తెలియదు, ఏమీ తెలియదు. ఆ పాపను వాళ్ళ అమ్మకి అప్పచెప్పాలని వెళ్తాడు. సో అలాగా మనం కూడా దయాదులైనప్పటికి కూడా వాళ్ళు వెనక్కి వస్తూ ఉన్నారు, వాళ్ళ నుంచే వచ్చింది అనేది అక్కడ ఇది. సో అని అంటారు. ఏ కంట్రీ నుంచి వచ్చిందని చెప్పలేము. విసినిటీలో పాకిస్తాన్ ఉంది కాబట్టి పాకిస్తాన్ నేషనల్స్ అంటే వాళ్ళు ఏం చేసి ఉండరు, బట్ అందులో కూడా కొంచెం శాంతిని నమ్ముకునే వాళ్ళు ఉండరు కదా, వాళ్ళు చేసింటారు అని చెప్పి భావన. లేకపోతే మన దేశంలో నివసించే పౌరులు మన ఆర్మీ బేస్ మీదకి, ఎందుకంటే మనం ట్యాక్స్ కడితేనే కదా వాళ్ళకి అవన్నీ సమకూరుతాయి. సో వీటికి బాంబులు అక్కడ ప్రయోగిస్తారు అంటే ఆ ప్రయోగించిన దానివల్ల ఏం మెసేజ్ తెలుపుతారు. సో డెఫినెట్ గా అది పాకిస్తాన్ నుంచి వచ్చిందని చెప్పొచ్చు. జనరల్ గా అయితే ఏ కంట్రీ నుంచి వచ్చిందనేది చెప్పడానికంటే డ్రోన్ చాలా తక్కువ బ్యాటరీతో ఆపరేట్ అవుతుందమ్మా. దాని గురించి కొంచెం చదవండి మీరు. సో ఇంట్రెస్టెడ్ గా ఉన్నారు కాబట్టి అదొక హాఫ్ అన్ అవర్ 40 minutes బ్యాటరీ ఉంటుంది అంతే దానికి. సో దాన్ని GPS తో ఆపరేట్ చేస్తారు. దానికి బ్యాక్ హోమ్ ఆపరేషన్ కూడా ఉంటుంది. మీరు ఇంట్రెస్టెడ్ అనుకుంటే ఒక 3-4 స్టూడెంట్స్ కలిసి ఒక చిన్న డ్రోన్ కొనుక్కొని ఎక్స్పెరిమెంట్ స్టార్ట్ చేయదు మీ కాలేజీలోనే మీరు చేయొచ్చు. అంటే జస్ట్ డ్రోన్ ఎలాగా పనిచేస్తుంది అని చెప్పి చూడటం కోసం. సో అదంతా చీప్ గా అవైలబుల్ గా ఉన్నటువంటి ఎక్విప్మెంట్ అనమాట. మేము మీకు చూపించిన వైట్ డ్రోన్ అరౌండ్ 2500 రూపీస్ అంత. ఒక 5 స్టూడెంట్స్ కలిస్తే ఒక డ్రోన్ కొనుక్కోవచ్చు. లేదు మీరు ఇంట్రెస్టెడ్ గా ఉన్నారంటే మీ హెచ్ఓడికి చెప్తే ల్యాబ్ లో ఒక డ్రోన్ ఏర్పాటు చేయడానికి చూడవచ్చు. సో చెప్పండి. సంబడి ఎల్సీ వాట్సన్ వాట్ అని ఒక వాదనమ్మా. దానికంటే ముందు చాలా మంది ఆర్ఎం పేజ్ అనే ఆయన అమెరికాలో ఎక్స్పెరిమెంటేషన్ చేస్తూ తద్వారా ఒక సిడబ్ల్యూ రాడాన్ని ఫస్ట్ కనిపెట్టాడు అని చెప్పి ఒక వాదన. సో అక్రాస్ ద అట్లాంటిక్ లో అటు సైడ్ ఇటు సైడు చాలా మంది క్లైమ్ చేస్తారు. బట్ ఏంటంటే మనం ఎక్కువ యూరోసెంట్రిక్ గా వెళ్తాం కాబట్టి వాట్సన్ వాట్ అని అంటాం. ఎందుకంటే ఆయన డెమాన్స్ట్రేటబుల్ సిస్టమ్ చేసి World War II లో ఉపయోగించి జర్మన్ బాంబర్స్ అంటే ఎయిర్ క్రాఫ్ట్ తో వస్తున్నటువంటి బాంబర్స్ అని పిలుస్తారు అనమాట. ఎయిర్ క్రాఫ్ట్ విత్ క్యారీయింగ్ వెపన్స్ బాంబింగ్స్ అన్నమాట. వాటిని ఆపేయడు అని చెప్పి వాళ్ళు క్లైమ్ చేసుకున్నారు అలైడ్ ఫోర్సెస్ ఆఫ్టర్ World War II. అందుకని క్రెడిట్ అంతా సర్ వాట్సన్ వాట్కి ఇచ్చారు. చెప్పండి ఇంకా. వెరీ గుడ్.
బ్లైండ్ రేంజ్ గురించి కొంచెం ఒకసారి చెప్పరా సార్?
సో బ్లైండ్ రేంజ్ గురించి మళ్ళీ చెప్పమంటారా? ఓకే. సో ఇంతకుముందు మీకు చూపించాను కదా పల్స్ అని. సో ఆ పల్స్ డ్యూరేషన్ ఉన్నంత వరకు, అంటే మీకు తెలుగులోనే చెప్పాలి అని అంటే తెలుగులోనే చెప్తాను. ఆ పల్స్ డ్యూరేషన్ అనేది, పల్స్ అనేది నీకు రేడియేట్ అవ్వాలి కదా, యాంటెనా నుంచి రేడియేట్ అయ్యే సమయం వరకు పల్స్ వెళ్ళదు కదా. ఆ పల్స్ వెళ్ళదు కాబట్టి యూ విల్ నాట్ బి ఏబుల్ టు డిటెక్ట్ ఎనీ టార్గెట్స్ అంటిల్ దట్ డ్యూరేషన్. సో ఆ డ్యూరేషన్ ఎంత ఉంటుందో దానికి ఈక్వలెంట్ టైం, దానికి ఈక్వలెంట్ రేంజ్, అంటే ఆ టైం 1 microsecond అయితే దానికి ఈక్వలెంట్ రేంజ్ 2r = c/τ ప్రకారం r = c/τ/2 అనేటువంటి ఒక ఫార్ములా ప్రకారం మీకు అది 150 meters గా వస్తుంది. అంటే 150 meters వరకు నీ రాడార్ యాంటీనా ఏమి చూడలేదన్నమాట. సో రాడార్ ఈజ్ ఆల్సో నోన్ యాజ్ ఎన్ ఎలక్ట్రానిక్ ఐ. సో ఆ కన్ను 150 meter అవతలని చూడడం ప్రారంభిస్తుంది, కానీ 150 meter లోపల ఏమి చూడలేదు. సో అలా కాకుండా కంటిన్యూస్ వేవ్ రాడార్ ఉంది అని అంటే అది అంతా దగ్గర, ఈవెన్ 1 meter దగ్గర కూడా చూడొచ్చు. ఇప్పుడు మన వందన వాట్ ఎవర్ షీ ఎక్స్ప్లెయిన్ టు యూ ఆర్ ఆల్ కంటిన్యూస్ రాడార్స్. అండ్ దెన్ ఈవెన్ హార్ట్ రేట్, బ్రీత్ రేట్ విత్ 0.3 meters. అంటే 0.3 meter అంటే మీకు ఎంత 30 centimeters డిస్టెన్స్ లో ఒక పర్సన్ నిల్చుకున్నా కూర్చున్నా కానీ అతని హార్ట్ రేట్, బ్రీత్ రేట్, వెరీ సెన్సిటివ్ పారామీటర్స్ ని కూడా, డాప్లర్స్ ని అబ్జర్వ్ చేయగలిగేటువంటి పరిస్థితి ఉంది అని అంటే దేర్ ఇస్ నో బ్లైండ్ రేంజ్ ఫర్ దీస్ 2 రాడార్స్. ఓకే, బ్లైండ్ రేంజ్ అనేది ఓన్లీ పల్స్ రాడార్స్ లో మాత్రమే వస్తుంది. ఇంకొక అప్లికేషన్, మీకు ఇంట్రెస్టింగ్ అప్లికేషన్ చెప్తాను బ్లైండ్ రేంజ్ గురించి వచ్చింది కాబట్టి. అదేంటంటే మన మిసైల్స్ ఉన్నాయి కదా, ఇప్పుడు వార్తల్లో కూడా 200 సైలోస్ ఏవో చైనీయులు వాళ్ళ దేశంలో చేస్తున్నారని చెప్పి చెప్తున్నారు అనమాట. సైలోస్ అంటే ఏంటంటే దే విల్ బి పుట్టింగ్ దేర్ న్యూక్లియర్ హెడెడ్ ఏమంటారు ఇంటర్కాంటినెంటల్ బ్యాలిస్టిక్ మిసైల్స్, అండ్ దెన్ ఇఫ్ దే ఆర్డర్ దే కెన్ గో అండ్ హిట్ ఎనీవేర్ ఇన్ ద వరల్డ్ అన్నమాట. 200 సైలోలు వాళ్ళు ఎందుకు చేస్తున్నారో ఏమి తెలియదు, ప్రపంచం మీద ఆధిపత్యం కోసం అని చెప్పి మనం అనుకోవచ్చు. సో ఆధిపత్యాన్ని సంపాదించడం కోసం వాళ్ళు దే ఆర్ ట్రైంగ్ టు డూ ఆల్ దిస్ కైండ్ ఆఫ్ స్టఫ్ బికాస్ ఆఫ్ 100 years ఆఫ్ దేర్ చైనీస్ కమ్యూనిస్ట్ పార్టీ అండ్ ఆల్. సో ఆ కాంటెస్ట్ లో నేను ఏం చెప్పదలుచుకున్నానంటే, ఆ మిసైల్ ఏదైతే ఉందో మన దగ్గర ఉన్న అగ్ని-1 కానీ అగ్ని-2 కానీ పృథ్వీ కానీ వాటిల్లో ఒక ఇంపార్టెంట్ కాంపోనెంట్ ఉంటుంది, అందులో ఒక రాడార్ ఉంటుంది అనమాట. ఆ రాడార్ ఎప్పుడు వస్తుంది అని అంటే, సపోజ్ ఫర్ ఎగ్జాంపుల్ ఫిక్షనల్ గా మీకు చెప్తాను. సో మన మీద ఎవరైనా దాడి చేశారు, మిసైల్ దాడి అంటే మనం ప్రతి దాడి చేస్తాం. ఆ ప్రతి దాడి చేసినప్పుడు వాళ్ళ కంట్రీలో, వాళ్ళ ఎక్స్ కంట్రీలో మనం వై సిటీని టార్గెట్ చేసామనుకోండి, ఎందుకంటే నేను అక్కడ మనం టార్గెట్ చేస్తామని కూడా నేను మాట్లాడకూడదు, బీయింగ్ సిట్టింగ్ ఇన్ రెస్పాన్సిబుల్ పొజిషన్, బట్ వీ హ్యావ్ ఏ మ్యాండేట్ దట్ అన్లెస్ సంబడి అటాక్స్ వీ డోంట్ అటాక్. సో ఆ సిచ్యువేషన్ లో ఎక్స్ కంట్రీలో వై సిటీని మనం టార్గెట్ చేసినప్పుడు వై సిటీ గ్లోబల్ కోఆర్డినేట్స్ దాని మీద ఉంటాయి. సో అలా కాకుండా ఎయిర్ టు ఎయిర్ వార్ జరుగుతుంది. మన రఫేల్ యుద్ధ విమానము ఒక మిసైల్ ని లాంచ్ చేసింది, ఫర్ ఎగ్జాంపుల్ బ్రహ్మోస్. సో అవతల పార్టీ ఏదర్ ఈస్టర్న్ నైబర్ కానీ వెస్టర్న్ నైబర్ ఎయిర్ క్రాఫ్ట్ మీదకి వెళ్తుంది. అది వెళ్తున్నప్పుడు వాళ్ళు మెనూవర్స్ తీసుకుంటారు, ఎయిర్ క్రాఫ్ట్ మళ్ళీ మెనూవర్స్ తీసుకుంటూ అటు ఇటు తిరుగుతూ వెళ్తూ ఉంటుంది. ఆ ఫైనల్ స్టేజ్ ఆఫ్ ఎంగేజ్మెంట్ లోకి వెళ్ళినప్పుడు ఫస్ట్ 5 కిలోమీటర్లో ఏం జరుగుతుందంటే జిపిఎస్ నావిగేషన్, ఇనర్షియల్ నావిగేషన్ సిస్టమ్ ద్వారా మిసైల్ అక్కడికి వెళ్ళిపోతుంది. వెళ్ళిన తర్వాత లాస్ట్ 5 కిలోమీటర్స్ లో ఆ నావిగేషన్ ప్రాసెస్ ఏమవుతుందంటే హ్యాండ్ ఓవర్ చేస్తారు, రాడార్కి చెప్తారనమాట, ఏమయ్యా ఇక్కడ దాకా వచ్చేసాము, ఇక్కడి నుంచి నువ్వే చూసుకోవాలి, ఎందుకంటే మా పరిధి దాటిపోయింది, దగ్గరికి వచ్చిన తర్వాత నువ్వే బాగా చూడగలుగుతావు అని చెప్తారు, అందుకని నువ్వు కంట్రోల్ తీసుకో అని చెప్పి మిసైల్ దానికి చెప్తుంది అల్గర్థం రూపంలో. సో రాడార్ విల్ టేక్ కంట్రోల్ ఓవర్ ఇట్. దట్ రాడార్ ఈజ్ ఎ పల్సర్ రాడార్. ఆ పల్సర్ రాడార్ కూడా కొంత బ్లైండ్ రేంజ్ ఉంటుంది. అంటే అజ్యూమ్ చేసుకోండి, ఎయిర్ క్రాఫ్ట్ దగ్గరికి వెళ్ళిపోయింది, ఎయిర్ క్రాఫ్ట్ పరిసర ప్రాంతాల్లో తిరుగుతూ ఉంది మిసైల్. సో అప్పుడు ఏం చెప్పుద్ది అంటే మళ్ళీ ఈ రాడారు, మహాప్రభు నేను ఇక్కడి నుంచి చాలా దగ్గరికి వచ్చేసి టార్గెట్ దగ్గరికి వచ్చేసాను, ఐ నీడ్ టు హిట్ ద టార్గెట్. అప్పుడు నా పరిధి సరిపోదు, నాకు బ్లైండ్ రేంజ్ అనేది ఉంటుంది. 150 మీటరు, ఇప్పుడు 1 మైక్రోసెకండ్ పల్స్ ఉపయోగిస్తుంటే 150 మీటరు, లేదా 10 నానో సెకండ్స్ పల్స్ ఉపయోగిస్తున్నాను అనుకోండి, అప్పుడు ఇంకా తక్కువ ఉంటుంది కదా. 100 నానో సెకండ్స్ ఉపయోగిస్తున్నాను అనుకోండి, అంటే ఏంటి 0.1 మైక్రోసెకండ్స్, అంటే 15 మీటర్స్. ఆ 15 మీటర్స్ దగ్గర ఉన్నప్పుడు అది ఏం చేస్తుంది అంటే, నేను ఏం చేయలేను కాబట్టి ప్రాక్సిమిటీ ఫ్యూజ్ అనే ఒక దానికి అప్పచెప్తుంది అనమాట. ఆ ప్రాక్సిమిటీ ఫ్యూజ్ ఈజ్ ఆల్సో ఏ రాడార్ విచ్ ఈస్ ఏ కంటిన్యూస్ రాడార్. దట్ రాడార్ విల్ కమ్ ఇన్ టు ఎగ్జిస్టెన్స్ అండ్ దెన్ సీస్ త్రూ. ఇఫ్ దెర్ ఇస్ ఎ టార్గెట్ ఇట్ గోస్ అండ్ ఎక్స్ప్లోడ్స్. అర్థమైందా బ్లైండ్ రేంజ్ స్టోరీ పాపం? ఇంకా ఇంకా ఎనీ క్వశ్చన్స్? సో నేను తెలుగులో కూడా చెప్తానమ్మా మీకు కావాలనుకుంటే. సో అదేమి తెలుగు అనేది తెలుగులో చెప్పడము, తెలుగులో మాట్లాడడం అనేది తప్పు కాదు. ఏ భాష అయినా కరెక్ట్గా వస్తే రెండో భాష ఖచ్చితంగా వస్తుంది. మన ఇండియన్ లాంగ్వేజెస్ లో ఏ లాంగ్వేజ్ మీకు పర్ఫెక్ట్ గా వస్తే ఇంగ్లీష్ లాంగ్వేజ్ ని చాలా సులభంగా నేర్చేసుకోవచ్చు. సో అది రాదు అని మీరు ఇంకా అనుకోలేదు. నెక్స్ట్ ఇంకెవరైనా ఏదైనా ప్రశ్న ఉందో అడగండి. యూ ఆస్క్ సమ్ క్వశ్చన్స్ సో దట్ లెట్ దట్ బి డిస్కషన్ విత్ దేర్. So any more questions? Nobody is doing.
ఇప్పుడు మన ఎనిమీస్ మనల్ని ఐడెంటిఫై చేయకుండా డ్రోన్స్ కి ఏమైనా మెటీరియల్ యూజ్ చేయగలమా సార్?
ఎనిమీస్ ఐడెంటిఫై చేయకుండా డ్రోన్స్ కి మెటీరియల్ ఉపయోగించేది నితీష్ కుమార్.
ఎస్ సార్.
అంటే ఏ విధంగా ఇప్పుడు డ్రోన్ ని మనం పంపించే డ్రోన్ పంపిస్తే డ్రోన్ ని మన ఐడెంటిఫికేషన్ తో సంబంధం లేదు నాయన. డ్రోన్ అనేది టిపికల్ గా కెమెరాని ఎక్విప్మెంట్ చేసుకోవచ్చు. డ్రోన్ లో ఇంకా రకరకాల సెన్సర్స్ పెట్టచ్చు. ఆ సెన్సర్ డేటాని ఫ్యూజ్ చేయొచ్చు. రకరకాల వ్యవహారం ఉందన్నమాట డ్రోన్స్ లో. సో ఆ డ్రోన్స్ అనేది చిన్న సైజు నుంచి పెద్ద సైజు దాకా ఉన్నాయి. 100 grams నుంచి 1 ton దాకా ఉన్నాయి అన్నమాట. 100 kgs వరకు, 0.1 ton, 1000 kgs వరకు ఉన్నాయి అన్నమాట.
అంటే సార్ అప్పుడు పుల్వామా అటాక్ జరిగినప్పుడు మన ఎయిర్ క్రాఫ్ట్ పాకిస్తాన్కి వెళ్ళినప్పుడు డిటెక్ట్ చేశారు కదా సార్?
అవును నాయన, ఎయిర్ క్రాఫ్ట్ పాకిస్తాన్కి వెళ్ళినప్పుడు డిటెక్ట్ చేయడం అంటే అప్పుడు అందరూ హై అలర్ట్ మీద ఉన్నారు. ఆ హై అలర్ట్ మీద ఉన్నప్పుడు ఎయిర్ క్రాఫ్ట్ డిటెక్ట్ చేసుకోగలిగారు. ఎయిర్ క్రాఫ్ట్ లార్జర్ RCS డిటెక్ట్ చేయగలిగారు. డ్రోన్స్ అనేవి అందుకనే కదా ఇప్పుడు వాళ్ళు వేరే కుతంత్రం పని చిన్న దాంతో వచ్చారు. మీకు చరిత్ర తెలియదు, 1989లో దే కేమ్ త్రూ, అంటే ఇండియాని 1000 ముక్కలుగా చేయాలనేది వాళ్ళ యొక్క భావన అనమాట. అంటే వాళ్ళు సుఖంగా ఉండకూడదు అని. అది 1971 వార్ తర్వాత వాళ్ళు భావించారు. ఆ భావించింది 1989లో ప్రవేశపెట్టారు అనమాట. అప్పుడు చాలా ఇబ్బందులు జరిగి ఇప్పుడు ఏదైతే కాశ్మీర్కి ఇంత ఆర్టికల్ 370 రద్దు అవన్నీ జరిగిన ప్రదేశంలో చాలా ఘర్షణలు జరిగి చాలా మంది ప్రజలు అక్కడి నుంచి వేరే ప్రాంతాలకు వచ్చేసారు అనమాట. సో అది చాలా హిస్టారికల్ గా ఉన్నటువంటి ప్లేస్. వాళ్ళు దాన్ని కావాలంటారు, మనం వాళ్ళకి ఇవ్వము. సో ఆ విధంగా అనమాట దానికి సంబంధించి. సో మీకు టెక్నికల్ గా చెప్పాలి అని అంటే ఇప్పుడు అందుకనే డ్రోన్స్ రూపంలో, సరికత్తు రూపంలో వస్తున్నారు. ఇప్పుడు హైదరాబాద్ లో లుంబిని పార్కు, తర్వాత ఇంకొక చాట్ ఈ గోకుల్ చాట్ అనేటువంటి ప్రదేశంలో 2007 అనుకుంటాను, కరెక్ట్ గా నాకు గుర్తులేదు, అక్కడ బాంబింగ్స్ జరిగాయి అన్నమాట. అలాగా వాళ్ళు ఎక్కడ ఢిల్లీలో జరిగాయి. అలాగా 2008లో మీరు చూసుంటారు కదా, 2008లో మీరు చిన్నపిల్లలుగా ఉన్నప్పుడు చూసుంటారు. సో ఒక యుద్ధమే జరిగింది అనమాట. దే కేమ్ త్రూ, పాకిస్తాన్ నేషనలే వచ్చాడు కదా, వచ్చి కసబ్ అనేవాడిని గుడి కూడా తీసేశారు మనం. సో వాళ్ళకి స్ట్రాంగ్ ఎవిడెన్సెస్ ఉన్నాయి, వాళ్ళు వచ్చి మన మీద అటాక్ చేయడానికి చేశారు. సముద్ర మార్గం ద్వారా వచ్చి ముంబై మీద విపరీతమైన అటాక్ చేశారు అనమాట. తాజ్ హోటల్లో అటాక్ చేశారు, చాలా మంది మీద, ఇంకా చాలా మందిని చంపేశారు. సో ఇట్ ఈస్ హ్యాపెనింగ్, ఇట్ హ్యాస్ బీన్ హ్యాపెనింగ్. సో దాన్ని ఇది చేయడం కోసం లాస్ట్ 7 ఏళ్లుగా చాలా తక్కువ జరిగాయని చెప్పుకోవచ్చు. అంటే ఐఎమ్ నాట్ ఎ పొలిటీషియన్, బట్ వాట్ ఐ వుడ్ లైక్ టు సే ఈస్ పటిష్టమైన భద్రతని ఏర్పరిచి వాళ్ళు ఆ విధంగా తీసుకొని వచ్చారు కాబట్టి ఆ విధంగా జరిగేది. సో అందులో భాగంగా ఎవరికి కనిపించకుండా లో రిస్క్ లో ఇటువంటి డ్రోన్స్ ప్రయోగించారు. ఇప్పుడు దానికి కూడా సమాధానంగా ఇప్పుడు DRDO వాళ్ళు డెవలప్ చేశారని చెప్తున్నారు కదా యాంటీ డ్రోన్ సిస్టమ్స్. అలాగే యాంటీ డ్రోన్ సిస్టమ్స్ కూడా డెవలప్ చేయొచ్చు. వీఆర్ ఆల్సో పార్టిసిపేటింగ్ ఇన్ దట్ కైండ్ ఆఫ్ టెక్నాలజీ డెవలప్మెంట్. లెట్ us see what will happen.
Yes sir, thank you sir.
Any more questions for anybody? టెక్నికల్ గా అడగండి. సో మీరు రాడార్ ఇంకా చదివినట్లేదు, ఎవరు రాడార్ని వదిలేస్తున్నారు. రాడార్ని కాదు, యాంటీనాస్ ని వదిలేస్తున్నారు, ఎలక్ట్రోమాగ్నెటిక్ వేవ్స్ ని వదిలేస్తున్నారు. ఎలక్ట్రోమాగ్నెటిక్ వేవ్స్, రాడార్స్ ని వదిలేస్తే ఏం జరుగుతుందంటే రాబోయే రోజుల్లో ఇట్లాంటి శత్రు దేశాలు మన మీదకి ఇటువంటి డ్రోన్లని ప్రయోగిస్తారు. అదే మీరు ఒక్కొక్క ఇంజనీరింగ్ కాలేజీలో ఒక్కొక్క డ్రోన్, యాంటీ డ్రోన్ డిటెక్షన్ సిస్టమ్ పెట్టుకొని దేశానికి అందిస్తే ఏం జరుగుతుంది అప్పుడు చెప్పండి. ఇంతమంది ఇంజనీర్లు అవుతున్నాం కదా మనము, దానికి సంబంధించిన టెక్నాలజీ డెవలప్ చేయడానికి మనకు ఓన్లీ సీరియస్నెస్సే కావాలండి. ఇందులో వనరులు, సపోర్టు అన్నీ వచ్చి తీరుతాయన్నమాట. వాటిల్లో పార్టిసిపేట్ చేసి ఇప్పటి వరకు మనం ఈ సాఫ్ట్వేర్ డెవలప్మెంట్ ఇది అది చేసుకుంటూ ఉన్నాం అనమాట. ఇట్లా ఇండిజినస్ గా చేసేటువంటి వాటి మీదకి మనం దృష్టి సాగించలేము. మన సిస్టమ్ కూడా ఆ విధంగా సమాయత్తం అవ్వాలని కోరుకుంటూ, విక్రమ్ గారు, కెన్ వి క్లోజ్ నౌ?
మంచిదండి. సో
థ్యాంక్ యూ.
ఆర్గనైజర్స్, ఐ జస్ట్ రిక్వెస్ట్, సో ఓట్ ఆఫ్ థ్యాంక్స్ లాగా మీరు ఏదైనా క్లుప్తంగా చెప్పండి. అండ్ దెన్ ఎవరెవరు క్వశ్చన్స్ అడిగారు నాకు కొంచెం పేర్లు ఏమైనా చెప్పగలుగుతారా? నితీష్ అడిగాడు, ఇంకా వేరే వాళ్ళు క్వశ్చన్స్ అడిగిన వాళ్ళ పేర్లు.
భవానీ ఒకళ్ళు అడిగారు సార్.
తర్వాత ఇంకా మొత్తం 4 అడిగారు. నితీష్, భవానీ, ఇంకా 2. డ్రోన్ ఏ దేశం నుంచి వచ్చిందని అడిగారు. ఎవరు?
నేనే సార్, నితీష్
నితీషేనా? తర్వాత మరి బ్లైండ్ రేంజ్ గురించి అడిగింది ఎవరు?
అడిగాడు.
సరే, ఓకే, అయితే సరే, మంచిది, ఓకే అండి. అయితే ఇంకా సరే అండి, మరి క్లోజ్ చేద్దామా?
ఓకే సార్. సార్ శ్రీహరి గారు, థ్యాంక్ యూ వెరీ మచ్ సార్. మా స్టూడెంట్స్ అడిగిన డౌట్స్ ని చాలా బాగా క్లియర్ చేశారు. ఫస్ట్ వాళ్ళకి అవేర్నెస్ క్రియేట్ చేశారు, ఎంత సీరియస్ గా తీసుకోవాలి, వాళ్ళు ప్రజెంట్ చదువుకుంటున్న సబ్జెక్ట్, దాని వల్ల యూజ్ ఏంటనేది చాలా బాగా ఎక్స్ప్లెయిన్ చేశారు సార్. ఐ హోప్ నెక్స్ట్ ఇంటర్న్షిప్స్ కి మా కాలేజ్ నుంచి కూడా కొంతమంది సీరియస్ గా ఎవరైతే ఇన్వాల్వ్ అవ్వాలనుకుంటున్నారో అలాంటి స్టూడెంట్స్ జాయిన్ అవుతారు మీ దగ్గర. రీసెర్చ్ వర్క్ లో కొంతవరకు అయినా పార్టిసిపేట్ చేస్తారని నేను ఎక్స్పెక్ట్ చేస్తున్నాను సార్. థ్యాంక్ యూ సో మచ్ సార్. అండ్ లాస్ట్లీ విక్రమ్ గారికి కూడా చాలా థ్యాంక్స్ సార్, మీ సపోర్ట్ కి. ఫస్ట్ ఆఫ్ ఆల్ అన్ని అరేంజ్ చేయడం దగ్గర నుంచి స్టూడెంట్స్ ని వాళ్ళ డౌట్స్ క్లారిఫై చేయడం వరకు మీరు చూపిస్తున్న ఇంట్రెస్ట్ కి చాలా థ్యాంక్స్ సార్.
మీరు నెక్స్ట్ టైం మీ స్టూడెంట్స్ తో సంగీతం పాడించవచ్చు కదండి, యాజ్ ఏ వెల్కమింగ్ సాంగ్ సరేనా? ఎందుకంటే మీ దగ్గర ఉన్నారు కదా ఆర్టిస్టులు, వాళ్ళతో కీర్తన పాడిస్తే బాగుంటుంది.
ఓకే సార్, ష్యూర్ సార్.
అంటే వచ్చిన గెస్ట్ కూడా మనం అదొక గిఫ్ట్ అన్నమాట, అంటే రిసోర్స్ పర్సన్ కి
నెక్స్ట్ టైం లైవ్ పాడిస్తాను సార్ డెఫినెట్లీ.
మంచిది. అదే
ఓకే
సార్ మీ ఫోన్ నంబర్ ఇస్తారా సార్ మాకు?
నేను సార్ మెయిల్ ఐడి మీకు ఫార్వర్డ్ చేస్తాను. సో దట్ మీకు ఏదైనా డౌట్స్ ఉంటే మీరు ఇన్ కేస్ సార్ తో కాంటాక్ట్ లో ఉండాలి అనుకుంటే త్రూ మెయిల్ కాంటాక్ట్ అవుదురు గాని. ఓకేనా విక్రమ్ గారు?
సరేనండి. ఇంకోటి ఫీడ్బ్యాక్ లింక్ పంపండి కొంచెము చాట్ లో.
ఓకే సార్,
చాట్ లో కొంచెం ఫీడ్బ్యాక్ లింక్ పంపండి. మీకు మెయిల్ చేశానండి, కొంచెం చూడండి, మెయిల్ లో ఉంది అది.
ఓకే సార్. ఓకే సార్. వన్ మినిట్ సార్, ఫీడ్బ్యాక్ లింక్ షేర్ చేసి క్లోజ్ చేద్దాం సార్. ప్రశ్న సార్.
మేడం కెన్ ఐ లీవ్ నౌ? శ్రీలక్ష్మి మేడం, కెన్ ఐ లీవ్?
ఓకే సార్, థ్యాంక్ యూ సార్.
థ్యాంక్ యూ.
ప్రశ్న సార్, మీరు మెయిల్ నుంచి ఒకసారి నాకు లింక్ చాట్ బాక్స్ లో ఉంటే షేర్ చేయండి సార్. మీకు మెయిల్ ఐడి ఉంది కదా మీ దగ్గర? మీ మెయిల్ ఐడి కాదు సార్, హెచ్ఓడి మెయిల్ ఐడి నుంచి లింక్ ఉంది, అది లింక్ ఒకసారి పేస్ట్ చేయండి.
ఈవెన్ వీకేఆర్ ఈసీ స్టాఫ్ మెయిల్ ఐడిలో కూడా ఉంది అది.
ఓకే సార్. అయితే
అది మీకు వచ్చింది కదండి, ఫీడ్బ్యాక్ లింక్ అని పంపించాను కదా, రాలేదా?
ప్రశ్న సార్, నేను షేర్ చేయనా మీకు? హెచ్ఓడి మెయిల్ నుంచి స్టాఫ్ మెయిల్ పంపిస్తాను.
నాకు పంపించారు సార్ విక్రమ్ సార్.
చూడండి మరి, అదే ప్రసన్న గారు మరి చూడండి, అందరికి పంపించాను. ప్రసన్న గారు, రాజేంద్ర గారికి కూడా పంపించాను. సరే, ఎవరో ఒకరు చేయండి, మీ దగ్గర ఉంది కదా. సరే, ఓకే, మంచిది. ఇక నేను కూడా వెళ్ళిపోతున్నాను, సైన్ అవుట్ చేస్తున్నాను.
స్టూడెంట్స్ అందరూ చాట్ లో మీకు ఫీడ్బ్యాక్ లింక్ ఉంది, ఒకసారి ఫిల్ చేయండి నాన్న.
మేడం, శ్రీలక్ష్మి మేడం.
సార్ చెప్పండి.
విక్రమ్ గారు ఉన్నారా?
సార్ లీవ్ అయినట్టున్నారు సార్ ఇప్పుడు. సార్ లీవ్ అయ్యారు సార్.
ఓకే మేడం.